So my protein project is on the kras protein, and the mutation which changed glycine to the amino acid aspartic acid or cysteine. So kras protein is part of a signaling pathway known as the RAS/MAPK pathway. It can be turned on and off by binding to different molecules. The kras protein is a GTPase, so it converts GTP and GDP molecules to become active and inactive, and vice versa. The protein binds to a GTP molecule to turn on and signal a cell when to grow and divide or differentiate by taking on specialized functions. The protein turns off by converting GTP to a different molecule, GDP. In other words, GDP inhibits the protein from relaying signals to the cell's nucleus. The KRAS gene in the nucleus is what gives the protein instructions to carry out in the cell. This gene is classified as an oncogene, since it can potentially make cells cancerous, since KRAS proteins signal the cell when to divide, proliferate, and specialize. The KRAS protein is a transduction protein because it reacts to chemical stimuli in the signaling pathway to tell the cell when to carry out cell division and specialization. So, the KRAS protein is located in the plasma membrane as it acts like a molecular switch. In the signaling pathway, EGF, or epidermal growth factor, binds to its receptor, thus activating tyrosine kinases. Then, the KRAS protein binds to GTP molecules to become active and transduce a signal to the nucleus. This signal is sent to the nucleus through MAPKs, then P13Ks, and AKTs. The protein is synthesized in cytosol. Furthermore, the protein belongs to a family of proteins that also bind to GTP to become active, known as the RAS superfamily. These proteins are found in mammals, found in all animals, but not all animals, but they're typically found in animals, specifically mammals. So this mutation makes the protein more active because the GTPase becomes inactivated, which makes the KRAS protein signal unable to turn off. Thus, this increases the activity in the cell since the off switch does not work. The main functional groups present in the original amino acid chain are carboxyl and amine groups. The side chain only contains a hydrogen atom. It does not contain a chiral carbon unlike the other amino acids. Thus, it has more space and can fit in spaces that other amino acids cannot, which makes glycine unique. Because of its small side chain, it can exist in both hydrophobic and hydrophilic environments. Glycine is characterized as ambivalent and nonpolar, although some sources classify it as hydrophobic because of its high flexibility and location inside the protein coil. It is the smallest of the 20 amino acids that make up proteins. So, also, glycine is capable of forming hydrogen bonds with water as well as with other hydrophobic chains. The new mutated amino acid side chain is either cysteine or aspartic acid. The main functional groups of cysteine are hydroxyl and thiol. Cysteine is considered to be polar by some and hydrophobic by other sources. The main functional groups of aspartic acid has two functional groups, amine and carboxyl. It is classified as polar and contains two carboxyl groups, making it the most acidic out of all the amino acids. Aspartic acid is charged and therefore often forms salt bridges, whereas cysteine forms hydrogen bonds and disulfide bridges through redox reductions between thiol groups. The mutation to the KRAS protein occurs in the precancerous stage and can be used as a marker for treatment early on. They form in lesions in the pancreas where neoplastic cells have not yet invaded. They are labeled as pancreatic intraepithelial neoplasia and rarely become invasive. The KRAS mutation itself is not a definite marker for tumors, but occur in over 90% of pancreatic carcinomas. So, the limitations of my model are that it only represents the quaternary structure of a protein, meaning it does not represent the specific amino acid sequences, although I did show like the location of glycine and the mutation. It also doesn't show like the individual bonds between R groups as well as the property of those bonds. And it only shows the coils and switches that make up the specific protein.